back to chemistry. Okay, cool. I hope this has also given some of you some extra time to stretch your legs and grab more coffee or whatever you need. Awesome. Okay, so coming back to the electronic structure problem. Just a quick reminder, this was the electronic Hamiltonian after the Born-Oppenheimer approximation. And you essentially want access to the lowest energy state of this Hamiltonian, the lowest energy and the lowest energy state, trying to solve this eigenvalue problem. Okay. And now moving on to the first slide with all the complex math, right? So you've been introduced to second quantized notation in the past, but essentially the Hamiltonian that I showed on this slide can be expressed in terms of fermionic creation and annihilation operators, okay, which satisfy these fermionic commutation relations, okay. And these sets of commutation relations are different from the rules that qubits follow, and so when we basically need to transform this fermionic Hamiltonian into a qubit Hamiltonian, okay, one that's expressed in terms of Pauli matrices or Pauli operators. Okay, so this fermionic Hamiltonian needs to be mapped into a Hamiltonian that can be expressed as a linear combination of multi-qubit Pauli strings. Okay, and Antonio yesterday discussed a bunch of different mapping schemes, which I won't describe in full length for the interest of time today. But just to give you a flavor of how this mapping works, you're essentially mapping, for instance, in the Jordan-Wigner scenario, you're mapping whether an orbital is occupied or not with a qubit. Okay, and often you'll have the question of how many qubits do you need for the simulation of XYZ molecule, right? Samarium hexaboride or something more complex. And so the question isn't quite answered by the molecule itself, but rather the number of orbitals you want to consider in the simulation of that molecule. So in general, if you had m electrons and n spin orbitals, okay, so I'm highlighting spin here, so orbitals which are spin degenerate, that problem is going to be mapped onto n qubits. Okay, so this is in general how many qubits one needs, right? And then you've also been introduced to, I think, some ideas regarding how you can optimize that, and I'll discuss that in a bit once again. But given that Hamiltonian that I showed in the previous slide, given this qubit Hamiltonian, or even working with the fermionic Hamiltonian, exact diagonalization is very hard, and so one has to rely on some other methods. And one example of that is the variational quantum Eigensolver, okay, which basically it's based on the variational principle. And this is. Let me also clarify that this is also a method that's used in computational chemistry run on classical computers. Okay, you have a Hamiltonian and you're trying to find its lowest energy state. And basically what the variational principle tells you is that the energy of any parameterized trial wave function, and by trial I mean a guess to the ground state, that energy is going to be have a lower bound, and that's going to be the exact ground state energy of that Hamiltonian. Okay, so let me actually spend some time proving this to you, since it's actually quite important and useful. So basically, you're given a Hamiltonian, and basically you want its energy eigenvalues and its eigenstates. Specifically, you want this for n equal to 0. Okay, and then you have a guess that you want to prepare, right? And this is parameterized by some set of theta. Okay, and this can be something you might parameterized even even in your classical program. And okay, so for this guess, you have an associated energy, which is the energy of the guess, and this is going to be equal to omega guess, right? And basically, you can express this as a linear combination of the different eigenstates of the Hamiltonian. Okay, so what does that mean then? This means that right? Okay, and if this forms an orthonormal basis, you basically are going to end up with only cases, non-zero terms when n is equal to m. So you have a n square okay. And this I said was because right, and this is basically oops. Okay. Try and squeeze this in here. Okay. And now E0 is the lowest energy state, right? It's the lowest energy. So this is going to be greater than okay. And then this is basically equal to 1. So this is going to be just E0. Okay. So that's the variational principle. And I hope that made sense.
Hey, Abhinav.
Yeah.
Hi, we just have a couple of people in the chat that are having some difficulty reading the red on the black background. If it's possible to write in white, that might be
Perfect.
better for the next time you do some whiteboarding. Additionally, we do have Brian Igmanson is back in action for hosting duties. So I'm actually going to pass off the hosting duties to him. So you'll be dealing with Brian for now, and I'm sure the crowd is going to go wild. So if you want to just remember to write in white next time, and I'll be passing it off to Brian on the back end, but you can go ahead and continue your lecture.
Sure.
Cool. Thanks, Abhinav.
Yep. Thanks. Thanks, Susie. Oh, that's too bold, right? Is this better? I hope so. If it is, please point it out. If it's not, okay.
Yeah, I think a brighter color is better. I think that looks better right? For me as well. Okay. Yeah.
Cool. Awesome. Okay. So how does the variational quantum eigensolver work? Well, the first step is always mapping the problem onto Pauli strings. So transforming your fermionic Hamiltonian into a qubit Hamiltonian, and then you want to prepare these guess states, so if you weren't using a quantum computer, you would basically have, for instance, some matrix representation of this, and then for every guess state, you would have to then measure an associated energy, which would also involve some large matrix multiplication, right? And these are tasks that are going to be hard as the system size gets larger and larger. So that stuff we want to delegate to the quantum computer, the preparation of the guess state and the measurement of the energy. and once the energy is measured, you supply that to some classical optimizer, which runs on your classical computer, and that's going to suggest a new set of theta values, a new set of parameters to prepare a new guess state. And then you apply this process iteratively till some convergence condition is met. Okay, and eventually, hopefully, if your guess is reasonably good enough, you converge to what the ground state is. Okay, so this is a very key slide. I know this has been covered yesterday, but just in case someone hasn't followed anything about the variational principle or the variational quantum eigensolver. Okay, so that's where we were. Thanks, Brian. And so addressing the first step once again, and now I'm going to basically take you through the different steps of the algorithm and connect them to many of the different errors that we discussed. Okay, so try and watch out for those connections. So basically, once you map your fermionic Hamiltonian onto qubits, you essentially have examples like this, and this is an example of a 4-qubit Hamiltonian. And what this notation basically means is a tensor product of Pauli matrices, where this is essentially sigma. This could be been written like this. All right, where this acts on the first qubit, the second qubit, third qubit, fourth qubit. All right, and these I'm going to refer to as Pauli strings. Okay, so one aspect of this is that the number of non-identity single qubit operators. So the number of so those operators which are not represented by i's, that represents the weight of the Pauli string. So this is a weight 2 Pauli string. This is a weight 4 Pauli string. This is also a weight 4 Pauli string. Okay, why is this relevant or important? Because larger weight Pauli strings are increasingly sensitive to the measurement error. Okay, so if you had just an identity, then when you try and measure the expectation value, it doesn't quite matter whether you had your measurement counts flipped between zeros and ones, because it's all going to sum up to 1. But if you want to measure an x, y, or z, then these will be more relevant and more important. So then this also has some considerations you might want to make on the choice of the mapping scheme from fermions to qubits. So for Jordan Wigner, typically, the weight goes as order n. For Bravik-Kitaev, it's order log n, a reduced order log n. So this can also affect how well your chemistry algorithm is working. Okay. All right. So then the next aspect was tapering of qubits. Can you reduce the number of qubits required in the simulation? Okay. So this is once again the same Hamiltonian that I have up there, with an example of with 4 qubits. And in this example, if you stare at this long enough, you'll notice that this operator is a symmetry of this Hamiltonian. And by that, what I mean is that it commutes with the Hamiltonian. Okay? Because if you look at only the first term, you only have basically x or I. Okay? And those commute from Pauli commutation relations. So in addition to this, what you'll also notice is that P0 not only commutes with the Hamiltonian, it also commutes with every individual term in the Hamiltonian. So what that means is you have Ix, Iy. Oops, I guess I went back to red. Sorry. You have XCZX, P0. You also have XC. YZ. Okay, and now we know the eigenvalues of P0. Okay, this is going to be plus or minus 1, and therefore you can essentially reduce this Hamiltonian now into H1 xiy plus or minus h, depending on which eigenvalue gets you the lower state, zzx plus or minus h3 cyz. Okay, so this is a very nice way of reducing the number of qubits you need for the simulation, and this is also very important as you work with noisy hardware. I'll emphasize that this is a reduction in the number of qubits with no approximations. There are alternate methods, but for instance, you might have discussed reducing the number of orbitals by freezing some of the core orbitals and not mapping those onto qubits. And those kinds of methods are approximate methods, but identifying symmetries in the qubit Hamiltonian and reducing this is exact. This does not change what your answer would have been. So that's this is basically one. This is just a highlight into how tapering works, or reduction of qubits. Okay, cool. So we've discussed about mapping and how hardware errors relate to different aspects of that. Now the trial state preparation. So the ansatz that I think Antonio focused on yesterday was a very classic ansatz. It's a very classic trial state, and that's what one often means by ansatz. It's a guess, and this is called the unitary couple cluster ansatz, and this is a very popular ansatz in computational chemistry. And essentially, what we're trying to do once again is we have this very large Hilbert space in which we want to find what the ground state is, right? And so working with this kind of ansatz offers the benefit that you're focused in on in a good space, and it also has some physical intuition. You can build off that kind of intuition, knowing where the structure of the ansatz is coming from. However, the catch here is that if you actually translate those T operators, those electron excitation operators onto qubits and then translate that into a circuit through tautorization, this leads to a very long gate count that for even modestly sized molecules, this gets beyond what a noisy existing quantum computer can do. Okay, so you can take a completely opposite approach where you keep the hardware limitations in mind, and you try and focus on a structure that that the hardware can do best. And this is what we are going to call hardware efficient trial states. All right. So if this figure is a little confusing, let me flesh it out a bit more in the next slide. Essentially, what we have are your consider 4 qubits: Q0, Q1, Q2, Q3, and then these are all initialized in the 0. So let's say we have some single qubit rotation here. We know how to do single qubit gates. Okay, for superconducting qubits, it's just driving on resonant microwave pulses. Okay, and now these single qubit gates, we're going to interleave with blocks that I'm going to call entanglers. So we can have one more layer. Okay, so that's going to be the general structure, and this can essentially keep going on. All right, And inside these blocks, I can have entangling gates between pairs of qubits. I'm showing this to be C-naughts, but we call these hardware efficient. So if there's some other gate that is more natural to the hardware, that could be in there. Okay, so the whole structure of this kind of ansad is really geared towards it's really geared towards what the hardware can do. All right, and now this is meant to be some parameterized guess, right? So different aspects of this could be parameterized. You could, for instance, have the theta rotations. These are single qubit. You could have a theta 1 here, a theta 2 here, a theta 3 here, theta 4, theta 5, theta 6. Okay, and then you could even parameterize, for instance, some aspects of your entangler gate. If you didn't want a full C0, you could have a partial entangling gate if that's what's more appropriate for your hardware. Okay, so one more nice aspect of this is that, well, you could ask how many of these blocks do you want to go. So I'm going to call this a depth 1, a depth 2, a depth 3. Okay. If I didn't have any of these entangling blocks, is this ansatz any useful for quantum computation? I hope the answer to many of you is a resounding no. Okay, because then you would only have single qubit rotations, which would then be a circuit that you can simulate efficiently on a classical computer. So there isn't any point in doing that. You need these entangling operations. Okay, okay. So what sets what depth you go up to? And I've already kind of alluded to this. It's called the coherence times. Okay, it is what is the coherence budget? What's the total time your circuit takes? And what fraction of your total coherence time is that? That's going to affect what depth you choose to go up to. All right. Okay. So I hope this basic idea was clear, that we're trying to work with states really geared towards what the hardware can do best. Okay. So I spoke of these single qubit rotations. In the lab later today, you're going to work with structures of these that are basically RY, RZ. So a Y rotation followed by a Z rotation. But in general, if you wanted an arbitrary single qubit rotation, you can construct that out of 3 Z rotations. And I'm sorry, this needs to be 2 and 3, and calibrated X90 pulses. Okay, so pi over 2 pulses, and it's fairly easy to go through and see that this structure can let you land up on at any point along this block sphere. Okay, so one aspect of this kind of operation or gate is that while the X90 pulses take a physical amount of time, the Z rotations you can actually do in software. Okay, and if you look at this block sphere, what this means is that a Z rotation is basically a rotation of the XY frame. It's completely equivalent. So if you translate that change in frame to all subsequent X and Y pulses, it will have the same effect of applying that Z rotation. Okay, so this is something you can do in software. This is what it's done in Qiskit as well. So these are then going to be perfect, and they'll have 0 physical time. So in only using these 2 X90 pulses, pi over 2 pulses, you can construct an arbitrary single qubit rotation. Okay, which is going to be parameterized by these 3 angles: theta 1, theta 2, theta 3. So 3 angles per single qubit block. Okay, but really, I mean, this is one possible choice. In this whole approach, you have a host of different options to choose as your variational parameters. You could choose the pulse envelope. You could choose the pulse shape. You could choose the pulse length, the amplitude, even the phase of these. All of these can be chosen as variational parameters, which will basically be updated every iteration. Okay, Right. So as I said, this is basically a sequence of interleaved arbitrary single qubit rotations, and then these entangling blocks that are composed of, what's naturally available to your hardware. To emphasize once again, the depth, the number of these layers that you have, that's going to be set by the available coherence time. And then if you want, for this kind of a structure where you don't parameterize any of the entanglers, but you only have you're only parameterizing the single qubit rotations, there you're going to have a total number of variational parameters that go linear in the number of qubits and linear in circuit depth. Okay, so the longer the circuit, the more number of variational parameters. And perhaps one thing I didn't emphasize enough was, why would one want to go longer? In general, the longer you go, the more of the Hilbert space you're able to access. Okay, so it's basically this competition between the available coherence that you have and how much circuit depth you need to be able to access your ground state. Okay, so one flavor of errors I spoke about were coherent errors, right? So an example I gave you was over rotations and under rotations. If you wanted to perform a 90-degree rotation, and instead what you applied was 89.5 or 90.5 degrees, does that affect the success of the algorithm? That's definitely important for some. With this kind of structure, and as opposed to the universal, the unitary couple clustered ansatz, for this kind of structure, you have some robustness, because say, for instance, you intended to do a 90-degree rotation on this qubit, right? And it was something else. The optimization is kind of self-correcting. The 90 degrees doesn't really mean much for the optimizer. It's just a label. It's just going to correct it so that difference gets accounted for. So this is really nice that you have some robustness to coherent errors. And what becomes more important for these kinds of trial states are leakage errors. Of course, you still want to be in your computational subspace, but also incoherent errors. That's going to be important. Okay, so let's talk about measuring expectation values. This aspect was about preparing your guess state, your guess wave function, and now this part is going to be about measuring. Okay, and let me now walk you through a very simple example. Okay, and I'm just going to come up with some example. This is not necessarily a fermionic Hamiltonian mapped. All right, and once again, this is a tensor product of two Pauli matrices. So this acts on qubit 1, this acts on qubit 2. Okay, and then we have some guess prepared. That's a linear combination of all the basis states. And I hope this answers the whole discussion and the questions on how do you measure expectation values. Okay, and you basically want to measure this, right? And this is basically going to be equal to so if I just focus in on only this term for now, okay, what does Z1, Z2, and phi do? Sorry. So if I take the notation that Z on 0 gives me 0, and Z on 1 gives me minus of 2. Okay, so and the eigenvalue is -1 here, it's +1 there. Right? So then this is going to give me alpha 0, 0. I have a 1 out there, so that's going to be a negative sign. It's going to be a minus beta 0, 1. It's going to be a minus gamma 1, 0. And then the -1, -1 are going to cancel. You get a plus sign again. It's going to be 1, 1. Okay, this is clear. So what this means is that this is basically going to be alpha square minus beta square minus gamma square plus delta square. All right. So what are the alpha, betas, gammas, and deltas? How do they relate to stuff that we measure? They're essentially the probability of 0, 0, the probability of 0, 1, the probability of 1, 0, and the probability of 1, 1. Okay, so this is what you measure. This is what you get from counts when you run an experiment. This is what you have access to. So this is an example of how you would measure a ZZ expectation value from experimental counts. Okay, I hope that was clear. Now let's talk about a slightly different example. Actually, something quite similar. So let's make that ZZ into a ZX, for instance. Okay, so we're going to what changes for a ZX? Okay, just once again, I was expressing this as alpha 0, 0 plus beta 0, 1 plus. Okay, so you're measuring in the Z basis. Okay, and that makes things a little trickier. So you essentially want this, but you have access to measurements in the Z basis. So you need to find some unitary which will transform X to Z. Okay, so if you plug this in here, what you basically get is and just moving things around a bit. Okay, so what does this mean? It means that now you can measure in the Z basis again, but then you have a slightly different circuit, a slightly different state. So how was psi constructed? Psi was constructed using some circuit like this, for instance. Say it was depth 2. Now we're going to basically add on a U2 on just qubit 2. So this was qubit 1, qubit 2. And this is basically a post-rotation. And then we can measure again. So many of you might know the identity that X is equal to H ZH, right? So this is basically just a Hadamard in this case. So if you had non-Z terms, if you had an X or a Y, you basically need to have some post rotations after your state preparation circuit. Okay, so that's what I'm showing in this step right there. All right. Okay. Now, if we go back to the original example that I had, which was what was it? It was 3ZZ. What about this term? Does this need another circuit? Okay, or can I measure these expectations with the same circuit? Okay, so basically, if you have qubit by qubit commutation. So the Z1 commutes with I1, Z2 commute. Then you can basically group them together. So in this instance, you don't need two separate circuits, right? Compare this with where you had some ZX plus IZ, right? Going from here to here, you needed a separate circuit because you needed the post rotation. But here it's very easy to go through, and I could probably do that for this example. When you want to measure right, this part applied on right. So because you have an identity here, there's going to be no dependence on sign. You're going to get just alpha 0, 0. You have a 1 on the second qubit. So this is going to be a minus beta 0, 1. The 1 for the first qubit doesn't matter because of the identity again. So the sign remains plus. And then here the delta is going to get flipped in sign. Oops. So when you have I1 Z2, it's basically going to be alpha square minus beta square plus gamma square minus delta square. Okay. So here there were no additional post rotations that one had to do. Does that make sense? And this is important. And working, I'm going really slowly over this because working through this will be very helpful for your lab and the problems that you have there. Right. Okay. So the next aspect of this is well shot noise. Even if you had the perfect ground state preparation, and if there was no decoherence and everything was perfect there, even then the measurement of your expectation value, this mean value, can have some error. Okay, and this is going to be related to the number of samples. This is the central limit theorem. So the standard deviation on this is going to go inversely with the root of the number of samples. So this is an example, and actually some experimental data I had a long time back when I was trying to measure the energy of a state prepared with a circuit, but all I was repeating were the number of shots. And then for a fixed number of experiments, if you plot out histograms that you get in the range of energy values, then you can see the standard deviation is very large when you have only 100 shots, but then gets extremely narrow when you increase that samples. Okay, so number of samples is also a very important aspect of trying to get this to work, and this connects very directly to what I'm going to talk about next. That is the efficiency of the classical optimizer. Okay, because based on these energy estimations at every iteration in the VQE process, you're going to have to make decisions based on whatever energy was measured, and the classical optimizer might fail if there's too much shot noise, right? Okay, so let me just discuss the classical optimizer, and then I think we'll be ready for another break. So this is an example of some energy landscape, okay, and as a function of some, I think some two parameters, right? So this axis is the energy, and then here you have, in this space, you have theta 1, theta 2, for instance. Okay, and what is it that you want to do? You basically want the optimization to get you there, to that nice minima point, and perhaps you start your optimization somewhere here. Okay, maybe this is your start, and hopefully you want this to be your end, right? One standard approach to run something like this is something called gradient descent, where at every step in the optimization, you try and measure the local gradient. Okay, so and that will tell you in which direction to move. And So if you're here, maybe a measurement of the gradient there will tell you to move in this direction for the next point, and so on. And this can get very tricky, because this is an example of fairly small small optimization problem. Just two parameters. But for instance, in the example of the hardware efficient trial state, I told you that the number of variational parameters goes as linear in number in circuit depth and linear in number of qubits. So that can get very large fairly quickly. So you need something that can operate with fewer measurements, because trying to solve the exact gradient is going to be very time consuming. But you also need something that can take some amount of stochastic noise, some amount of short noise, right, and can still make decisions. And one example I think that was briefly touched upon yesterday is the simultaneous perturbation stochastic approximation. So this is only really one example of a classical optimization method. There can be so many more, and identifying which one is actually appropriate or good is a very active area of research. This is something people are working very vigorously on. Okay, and to give you a sense of how this works, if you're if you're there in the optimization, what this does is it chooses one direction this way, it chooses an opposite direction this way, it measures an energy there, it measures an energy here. So irrespective of the dimensionality of the optimization parameter space, it only uses these two energy measurements to approximate the gradient, and then tries to make a decision on which direction to go based off that. So here in this case, it's going to land up, say, there. So it decided that this direction is good, so it's going to move a bit in that direction, and now it's going to choose a different random direction, perhaps there and there. And now this is the right direction, so it's going to land up here. And hopefully, if you're lucky, you land up there. But one very relevant aspect of all of this is local minima. This might be the global minima, but what if you get stuck, say, here? What if you get stuck there? What if you get stuck there? Right? How do you get out of that minima? This is also a very important aspect of optimization that can affect the performance of these kinds of variational quantum eigensolver-like algorithms. Okay, and then in this section, I just wanted to then finally talk about how many of these things affect the total runtime when you actually want to run this on hardware. So of course, it's the total number of energy estimations. So how many? So if you're taking the gradient descent approach, how many times do you need to measure the energy every iteration? How many Pauli strings do you have in your Hamiltonian? Okay, I mean, well, it's not exactly the number of Pauli strings. It's more to do with the number of groups, because every group is going to require a different set of post rotations, which means a different circuit that you have to run. That's going to affect the runtime. Then the total number of shots, that's also going to be important. And then one more aspect that I haven't touched upon is system initialization. I'm not sure how many of you paid attention to this, but typically in every circuit, you kind of start in the ground state, right? And then after you've run your entire circuit and measured it, what happens for the next shot? You're in some arbitrary state at the end of this measurement. In the most naive approach, you basically wait for your system to get back in the ground state. How can you do that? You can wait a few multiples of your T1 time. What was the T1 time? The T1 time was the time where if you prepared if you initialize your system in the one state, how much time does it take to decay back into the ground state, right? So that can set how much time it takes to run one shot. Okay, and that can be fairly long. If your entire circuit was only on the order of, say, 1 microsecond, in this scenario, you might have to wait, say, 200 microseconds. So a large part of the time overhead is just waiting. So there are smarter ways that, for the more interested readers, if you can look up qubit reset, there are smarter ways in which you can force the system back into the ground state much faster. And this is also going to affect the total runtime. When you actually want to run this on real hardware.